Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff, the awesome stuff, the AAS Journal Author Series. And I am super happy to have Don Dixon with us today. Hello, Don.
Hey, Frank. Thanks for having me.
Well, thanks for agreeing to talk about your very awesome AJ article. It's really cool. And Don, what's your geolocation?
Currently, I'm actually in Moreno Valley in Southern California. So I've been kind of working remotely, but I am a student at Vanderbilt University,
Cool.
which is in Nashville, Tennessee, for those who might not know.
Okay, very good. It is May 18th, 2023 as we record this. And is it June gloom yet in Southern California? Is it summer yet?
Yeah, I think summer is finally starting to pick up. It's starting to warm up finally over the last week or so. So I imagine it'll be getting pretty hot in a minute here.
So I'm in Phoenix, and the power switch is just about to be thrown. So we're already in the triple digits, but we haven't really hit the bang yet. But we will soon. So
yeah, Phoenix is rough.
Yes, very cool. And Don, what do you like to do for research?
So mostly what I focus on for research is stellar rotation and interacting binaries.
Cool.
So currently right now that's taking the form of rapidly rotating giants, which I'll talk a little bit about today, and also field blue straggler stars. So stars that exist outside of star clusters that might have been spun up by a companion. And so I'm looking into their angular momentum evolution. So those are the things I'm looking at.
Very cool. And that is going to bring us to this very awesome AJ article. It's open access, people. You can go get a copy for free in the open access there. Go get one. Rotationally driven ultraviolet emission from red giant stars. And Don, take us away.
Sure. Thanks. So as just a bit of an introduction, I guess I'll say, what's sort of the motivation for this? Why did we even bother to do this science? And so the idea quite simply is that you can actually get a lot of information out of rotation and activity as well, and you can actually learn a lot in the context of planets and in terms of binary stars. And so what we actually did here, and what's a little bit different about this, is that usually rotational and activity studies are limited to dwarf stars.
Yeah. Mm-hmm.
Right. But what we're looking at is we're looking at giant stars, and the reason why this is unique is that giant stars are almost always expected to not have basically no rotation, right? And the reason why this is true is that on the main sequence, you lose these particles through stellar winds, and in the introduction, I do mention that there you lose a lot of momentum because as you lose the particles and the stellar winds come out and they interact with the magnetic field, that steals angular momentum away, and the star actually slows down. So over the course of a lifetime, stars slow down significantly. For those of you who study stars a bit, you might have heard about this in the form of gyrochronology, right? The idea that you can age stars over the course of a lifetime by measuring their rotation.
Okay. Sure.
And so by the time you get to the giant branch, things have really slowed down.
Yeah.
And envelopes expanded. So if you remember the classical figure skater example from introductory physics, that means it slows down even further, right? So basically the end result of that is all giants are supposed to be not spinning basically at all.
Yeah.
However, it's been observed that some of them are spinning actually quite fast. So the threshold we use for that is 10 kilometers a second. And that's tends to hold true over many different literature that I've read, but the idea is that there's no way they should be spinning that fast at all.
Right.
But since they are, that opens up that opportunity to ask, well, how does rotational driven activity through dynamo action, how does that work for giants, right? And so that's kind of what we're investigating in this paper.
Cool. Very cool.
And so, maybe scroll down just a tad.
Looking at some apogee data.
Right, and I think this figure is perhaps a good place to start. This figure 1. Yep. And so basically, what we did is we looked at apogee, which is an infrared survey of Sloan Digital Sky Survey. It observes in the H band, which is moderately in the infrared, but not too far. And what we started with is we wanted to just do a very quick sample selection on a couple of catalogs that we were looking at. And so, this is when I first sort of started in grad school. So these initial catalogs were provided for me, but what we've done, as you can see in these two boxes here, is we've kind of grabbed the lower giant branch, which is that blue box, and then we also went higher up and tried to sample some of the red clump stars, which are colored red. And so you might say, well, why did you bother to do that? Well, the idea is we wanted to see if there were any differences in trend based on evolutionary phase, right? So what if we did the science and it actually turned out, oh, this is only valid for the lower giant branch star.
Yeah, it doesn't work on the upper, right? Yeah.
Exactly. So we decided to take this two sample approach.
Cool.
So basically everything in those two boxes is what we started with. So this is just very beginning, trying to sample some giants that we want to investigate this rotational activity relationships from.
Okay, looks like we got another clump over here too. Okay.
Yeah, it does extend further out, but yeah, and I guess maybe I can mention the yellow. So those are like secondary clump stars, and in our case, those are just considered contamination. I think they arise from higher mass stars that are just above the helium burning limit in the core or something like that. But don't quote me on that.
No, we're good. We're good. Okay, I'm with you.
So let's move on. I think the next figure kind of solidifies how we do the next sample. And this table, I think maybe we can perhaps skip. So what this table is designed to do, I'll just say, is this just showing the parameters that we use to describe the activity relationship that I'm going to talk about going forward. But there's not any science in it per se. It's just a header.
Right.
Of a file.
The actual numbers, there they are.
Yeah.
Figure 2.
Yes. So here we go. So here's what kind of shows the rest of the sample selection. And it's split in between two panels here, but let's start with the first panel.
Okay.
And so you see those same two blue and red bars that I was showing before. Yes. And then you'll see some actual markers in there that those the ones that I actually selected out. And so what's important about this figure primarily that's different from the other one is you've got this giant orange triangle looking thing here, right?
Yeah.
And so what's that? Well, that is to remove the rest of the contamination I'm getting from things that are not where they're supposed to be in this sort of spectroscopic HR diagram. So these things exist beneath the giant branch, and so they're not properly giants. They're not the things I actually want to study.
Okay.
So I actually want to remove a lot of those. And if you scroll down just a bit, you actually see that a lot of these things that are beneath the branch are actually variable star types. So I won't go through all of these star types.
Yeah, I was going to say.
There's a lot. Yeah, giant stars can actually pulsate and they can do all kinds of crazy things.
Oh, yes, they can.
So yeah, the orange things we're trying to remove, and this is just to show that we're tossing these because they might screw up our relationship.
But you still got a pretty good signal on, at least on the number of counts anyway.
Exactly. Yeah. So I think so we're still doing pretty good. This is what we end up with the 133 stars. And this will lead into the actual science case now that we've kind of built the sample.
Cool. I'm with you.
All right, so let's keep going just a bit.
You want to do matching distances?
Right there. And so the matching distances, again, I won't say too much on. I would just say that Galax pointing is a little bit worse than 2MASS, which is the building catalog for the science. And so this is just to show that once we do a matching distance of about 3 arc seconds, that pretty much gets everything that we want. So this is just to show how we did the cross match.
Okay. Cool.
What's much more important is this equation 1 over there, because this is the foundation of what we've done.
Yes.
And so what is this saying? What this is saying that the magnitude in the NUV filter minus the magnitude in the J-band filter is equal to this number plus or minus some error times the J minus K magnitude color. So this is a color-color relationship. So what does that mean? That means that you have some ultraviolet flux, and its ratio to some of the flux in the infrared has some linear form compared to the ratio of the J band and K band flux.
Got it. Okay.
And so what are we using this for? Well, it actually turns out that stars lie on a well-defined locus that's defined by this equation.
Yeah.
So if we look at stars and their displacement from that locus, that defines how much excess UV they have from what you would expect from their atmosphere.
Yes.
And so this is what we're using, because our argument is, well, they shouldn't have more than this, but if they do, perhaps it's because they have some kind of activity driven by rotation. And so that's the correlation we're looking for.
Cool. Very nice. Okay.
And you can skip 2 and 3. Those are just extinction laws. So that was important to make sure.
Yeah, they are. Well, it's important to take care of extinction, but figure 4 is going to get us to
right.
Population. Mm-hmm.
And this shows exactly what I was talking about. And so I'll talk a little bit about this figure because I think this is important. So that line that I was just describing, that's literally this equation split on there.
Is equation 1. Yep, right here.
Right. And all these little dots are the things in my sample. And so you've got the things with red edges, and those are just to kind of pick up the red clump stars, and things with black edges, which are the RGB stars. So basically those 2 boxes I was talking about before.
Got it. I'm with you.
And much more importantly, if you look at this color bar, you'll see that things are colored, the inner circles are colored by V sin I. So what you'll notice right away is that the things that lie way above this line tend to be bluer.
Yes.
Right.
Yes.
So, what this is telling us is that the V sin I, which is the rotation, the projected rotation that we get from apogee, seems to be very strongly correlated with how much UV emission you're getting. Nice. So it seems like we can draw this, follow the hypothesis we were saying before that, okay, rotation is driving activity in the form of excess UV emission. So that's the that's the idea.
Cool. And what is the arrow direction indicate?
That's reddening vector. It's just kind of to show how much you expect things in color space to change. Yeah.
Okay, I'm with you. Very nice plot. I like this one. Very good.
Yeah, I like this one too. I think it really kind of shows exactly what we're trying to get at here.
Right. Very cool. Okay, figure 4 onwards.
Right, and then so the next figure. We're
gonna get into some results.
Well, yeah, I think we better talk about these equations, and then I'll reference it to the figure. That'll be better. So this equation 4, what is this equation? So what this is this is actually the displacement from that line that we just showed in the previous figure. And it's a linear fit to this x value. What's the x value? The x value is the V sin I value. So it actually turns out that there's a linear functional fit to the displacement from that line versus the actual projected rotation in V sin I.
I'm with you. Yep.
So this is a rotational activity relationship. And so if you go down a little bit further.
Let's take a look at figure 5 maybe, or you want to?
We can actually, I think figure 6 might be the main, well.
Okay.
I wasn't gonna skip, but since it's there, let's go to figure 7. I think I'll double back because those aren't quite as important. But yeah, this is because this.
This is a good one. Okay.
And so what this line is these are the 3 functional fits that I was talking about. So you have the NUV excess as the displacement from that line.
Yep.
And you have the log space rotational velocity on the x-axis, and you can actually see the lines have a clear slope, right? They're slowly increasing, and the difference between the panels are the top panel are for things that we think are binary stars.
Okay.
The second things are field stars, so mostly single, and the last one is just the combination of the 2. But in all of them, you can see that they have a very similar slope. The binary stars have a higher y-intercepts, but we think that binarity may play a role in NUV excess, but that's for later science. But the main idea is that there's a very clear trend here, and the p-values are very low, and the correlation vectors are very high. So
Okay, good.
So the binary one is the lowest, but if you look at the filled one, we have a Pearson correlation coefficient of 0.7 and a p-value less than 10 to the -6. Yeah.
Million. Mm-hmm.
So, I mean, this is a very strong relationship. So this is what we're showing. Yes, in fact, giants are rotationally driven to have activity, and you can see it in the near ultraviolet with Galix.
Cool. Very cool.
Right. And so I guess we can maybe slowly go back up because I'll just briefly mention the two figures before, even though they're not nearly as important. But
let's try 5.
Yeah. And so basically what this is just showing is distributions of NUVXS and V sin I for both evolutionary state, the red giant branch and red clump stars, and the binary and filled stars, right?
Good.
And so what you can see is something I just mentioned before, is on maybe the top right panel, you can see that the variable stars clearly have more NUVXS. And remember, in magnitudes, things are backwards, which is why the y-axis is flipped. So they're brighter.
It's magnitudes.
Yeah, I didn't do that, by the way. That was done before I got to. And so, the variable stars, the binary stars, are actually have more NUVXS. So we do think binarity plays a role there. The red clump and red giant branch stars, there's also differences there. But we think that makes sense because as you evolve further into the red clump stars, you are less likely to get a binary, and our selection, I think, actually searches for lower masses, so you actually expect less ultraviolet excess there as well. So that's a little bit more complicated, but the basic idea is this is just kind of a sanity check, and things seem to
things are making sense there. And then figure 6, there's V side. Ooh. Histogram. Okay, cumulative distributions.
Right. And so this is kind of showing something similar. I think the main thing to look in this top panel here is you'll notice that the blue line, which represents our binaries,
right?
And you look at the dot on that blue line, which is the 95th percentile. Yeah.
Right here.
It's like way over here versus the field, which is the orange, and the total, which is the black. Being much more to the left at like maybe 60 or so. And what this is to say is that binary stars tend to spin faster. Indeed. Stars and binaries tend to spin faster, which is
kind of makes sense.
Yeah, it does, right? Because we actually think that the binaries have some influence in spinning up the star, right? Because they all shouldn't be spinning at all. So the idea is, well, how did they get to be spinning? We think the binaries have something to do with that. Yeah,
indeed. All right, and then we've got our distributions.
Right, and this is just sort of showing us a similar thing. The binaries are also top heavy in terms of ultraviolet excess. So all of these things are making sense, in the narrative. There's a clear rotation activity relationship that we can define with V sin I and near ultraviolet excess, and binaries seem to be skewed in the direction of having higher NUV excess. So
I'm with you. Very good. And then we covered figure 7. That's a beautiful figure.
And I think this table 2 is actually worth talking about just a bit. Not all of it, but the top, well, I'll say the NUVXS, the V sin I, and the metallicity may be important, right? So what is this? This is a Kendall-Tau correlation matrix. And basically what that says is you're looking for different trends between parameters. So the higher the number, positive or negative, that just implies a direction, the more important it is, right? The more important they are to each other.
And so like a 1 down the diagonal.
Exactly. When you go down the diagonal of a correlation matrix, it should all be 1 because they're perfectly correlated with themselves. So if you start with NUVXS and you go across, you'll see that the V sin I is actually quite high. It's at -0.1.
Yeah.
But the metallicity is not. It's like at 0.03. And so at the end of our discussion, I'll talk about some work we've been doing to kind of dig a little bit deeper into that. But basically, what I wanted to say about this table is one of the things that we sort of found in this table is that, well, maybe metallicity doesn't play that much of an effect, even though it actually does. And so if you look at table 3, which is
Okay.
oh yeah, if you have a question at all, sorry.
No, I'm
yeah,
churning a puzzle in my mind as you go through this.
right.
Okay.
And so you can see correlation matrices for the red clump stars versus the one I was talking about before,
Okay.
and the ones where I have radii from, which we got using angular diameters from a cross-matched paper. And you'll see, yeah, these ones have metallicity values which were a little bit higher. So this was a discussion in the first paper, but we couldn't do anything definitive about it. And so basically what I just wanted to say about these tables is that V sin I is very highly correlated, which makes sense from our relationship with NUV excess.
Yep.
But most of the other things aren't, even though we might expect metallicity to be. But this is just kind of putting some numbers on what we found. So
Very good. Very good. I like it. Kendalltown. Okay.
All right. And so now we're starting to get towards more of the discussion section where we talk about like, well, what does this science actually mean? What can you do with the science? Et cetera, et cetera. And so this equation is going to be important here. So I'll just say in a minute, this P crit equation. So what is that? This is actually the rotational period of a giant that is rotating so fast, the force of the particles at the edge of its envelope is equal to the centripetal force holding it together. So basically, if the star spins at this rotation, the star basically shreds itself apart. It's spinning so fast, it just rips itself apart.
Breakup.
Yeah, breakup speed. So stars can't rotate faster than this physically. They can't do it. They'll disintegrate. Yeah. And so that's going to be important in a minute. But if you scroll down just a little bit, we can talk about this first.
NUV versus P-rot. Okay.
Right. And so what I was just saying, for some of these stars, for about 77 of them, we have radiuses. And what you can do with a radius is using V sin I, you can convert that into a projected rotational period.
Yep.
Instead of velocities, now we have rotational periods, how long it takes for a star to rotate upon its axis.
I'm with you.
And the reason we were doing this is because we wanted to see if there was some saturation regime, which has been seen in M-dwarf. So basically, a star can spin so fast, it actually has less magnetic activity, or it saturates at some maximum, let's say, right? And so this is just kind of to show a double fit of the line, and then it tries to fit a flat line to some of the data points, and you see it's kind of off. It doesn't really match there, right? But this is an idea we tried, and we also tried it for Rossby number, which is basically just period divided by the convective overtime, the convective turnover time.
Yeah.
Yeah, so it's another metric for magnetic activity.
Sort of.
Yeah. And so now if you go to the next period, because both of these are kind of off, right? But if you go to...
Ooh, that's much better.
Yeah. Yeah, but this wasn't... Yeah, let's skip this one for now. But I will come back to that one, sorry. This one, yeah, this is what I wanted to show. This one actually fits much better, right? And so we were kind of excited to see this because what this looks like is not only do you have the saturation regime, you have a super saturated regime.
Yeah.
So you have these 2 points way over here, and they actually look like they have less magnetic activity. So the giants are spinning so fast that their activity actually decreased. Well, how fast are they spinning? Well, if you scroll down just a little bit, these 2 stars over here, they're spinning at significant percent of breakup. This one actually looks like it's spinning faster than breakup, which is not physically possible. I think this is just probably an error in the radii, or something that got carried over, but it's spinning near breakup. It's basically almost at breakup speed.
Right.
And so that kind of makes sense in the supersaturation argument, right? That's kind of
interesting. Okay.
Yeah. So we thought that was very interesting to see that.
Okay.
And so lastly, if you go back up, sorry for jumping around.
It's all good. It's all good.
Yeah. So you've got this figure, which is actually comparing to the M-dwarf. So this is what you're saying. Yeah, this looks cool. We think it looks pretty cool too. So the yellow points are actually M-dwarf stars.
Okay.
And the black lines actually show our relations for the giants, and they look kind of similar. And so what we're arguing that, well, perhaps magnetic activity may stem from the same place all across the HR diagram. So maybe the same things that are driving magnetic activity in M dwarfs are driving activity for giants.
Got it.
Which is, dynamo, which is kind of the dynamo physics explanation, right?
Right. Right. Well, that's good. It's a single mechanism.
Right. And so that's kind of the idea. So basically, we're trying to connect our giant activity to activity across the HR diagram. And it looks like there may be some similarities there.
Yeah. Yeah. Very good.
And then the last plot, I believe. Yeah, that one.
This one. Here we go.
And so basically what we've done so far is, hey, we've got an activity relationship in the form of ultraviolet excess and rotation. We've shown that it's similar to M dwarfs, and we've shown that there may have some saturation and supersaturation regimes. And so we're saying, okay, well, now that we have that relation, let's test it on something. So there's only a single point on this figure. And so what is that point? That's actually a black hole red giant binary that we plotted against our relationship. And the reason this was originally shared with me is because it was shown that there was some UV excess emission. And the question was, is the black hole feeding? Is this accretion?
Right.
Or is there just activity from the giant?
Right.
And what this is showing is that we can actually use this relation and we can say, oh, well, yeah, no, it could just be explained by activity from the giant, right? If the point was down here, we would if the point was up here, flipped axis, we would say, oh no, that's much higher than you would expect,
right?
From just rotation. So that's probably accretion going on or something like that.
Right. Very cool. Even with the error bar, it's pretty good.
Yeah, even with the error bars, it's pretty good. It's almost like a perfect fit. So
yeah, very cool.
And so that's just some application of the science. And so that's kind of the breakdown of the paper. We define the relationships. We say it may have some similarity to other activity of stars across the HR diagram. And you can actually use this for stuff, right? You can maybe apply this to systems and see if things make sense. So.
Love it. Very nice. Mm-hmm. Very nice. Don, I want to thank you so much for walking us through your very awesome article. Thank you.
Thanks for having me.
Sure. And you touched on it a little bit. And so I'll just push on a little bit. Where do you think we go with this over, let's say, the next 2 to 5 years? So is there additional data that can be coming off? Can we actually do direct UV photometry or spectra? Is there additional theoretical models that might be done to explain maybe some of the supersaturation or the lack of a metallicity dependence, apparent? And so where do we kind of go over the next couple of years on this topic?
Right. So I'm working on the follow-up to this paper right now. It took a little while, but we are in the writing phase, so most of the main results are done already.
Nice.
Which is why I can say, yeah, I know there is a strong metallicity dependence because we found it.
Okay.
And so the new data, right, is still apogee, but this data was primarily based from smaller catalogs that were given to me, and they were from DR14. And apogee, the data I'm working with for this follow-up paper is DR17. Okay. And so this paper was using 133 stars. The follow-up paper we use over 6,700 or something like that.
Nice. Oh, nice. Several magnitude more. Very
much better. So that's where I'm going with the science right now. And basically, the follow-up paper will have a metallicity dependence, and it'll also talk about how binarity plays a role, which we kind of hinted at in this paper, but we didn't quantify it too much.
Right. Very awesome. Cool. Well, I really look forward to seeing that one come out. AAS Journal, right?
Oh yeah. Maybe hopefully in the next couple of months. We're in the writing phase, so
I know how that goes.
You know how that goes.
Always takes a little longer than one thinks.
Yeah, exactly.
Very cool. Very cool. Well, Don, thank you so much once again for walking us through your very lovely article on this topic. And I really look forward to seeing it, your paper come out and seeing this field evolve over the next couple of years. So it'll be very nice.
Yeah, great. Thanks. I appreciate it.
Sure. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Take care.